body, not in the court, entirely secret body, will adjudicate any disputes between companies and government. The government can't see companies can see government. We'll see dispute settlement clauses have variants on the name, but whereas the European Court of Justice is indeed a court, transparent, who's on it. There may be confidentiality things. They tend to be moving away from Europe and getting closer to America. It's going to be if you're a catastrophe capitalist, you'll make lots of money. Most of us, of course, run the world. I'm already here saying, well, we will not take our share of the suffering, so we're going to cut whatever, 20% or something like that.
It is. So, as a child, yes.
So there's a sort of fakeism. People saying, well, the NHS is probably doing everything in quotes we can't afford. Forever.
Yes.
A decision.
This processing language kind of question to us. You didn't need a computer to I'm sure there's a few
they're not fights, but they know that our account is stupid and bigoted.
And also,
number of times when they say, look, we voted for this, I say, what we did, there is no we in this country anymore. That's true. And then it's going to get a lot worse. We haven't seen anything.
So where did you get the bus from?
There weren't that many people in the world.
I see.
Yeah, I mean, it was just before my time. I joined.
I think all you have to do is connect with everyone fully qualified newspapers and
All right.
things to adopt then having done that once, should then be
Yeah, because we want to wrap and say, we'd like to build. We did.
Yeah, sit wherever you like. Well, just sit here. Not your choice. Just wherever you feel comfortable.
Well, she's in Huddersfield. Except he's over saying she's
Okay, well, I'll wait you.
she's coming down. Well, I was online. And she's been two of them sometimes. She's very good. She just say like that virtual discuss keep up bring something I've never been tested. No, that's
Welcome to the new BCS office. I'm glad you all managed to get here. As you will know, having little trouble. Hopefully we're going to be here for some time now. I hope you like the new facilities. My name is Jonathan Bowen. I think I know quite a lot of you. I'm the chair of FACS. We've just had our AGM. I'm afraid in the time-honoured tradition, most of the officers haven't changed, so it's the usual crowd. I've been chair for a while. We've got John Cook here, the treasurer, and Roger Karski, who's our secretary, a number of other committee members here. So it's very, very nice to welcome David Turner here today. I'm sure a lot of you know David Turner. It's lovely to have such a big turnout here. And this is probably one of our biggest events we've had, David, so you know. So well done for attracting a good number. So I'm sure you all know that he's an expert in functional programming languages. He's contributed a lot of ideas in functional programming. So he will be telling you about that because he's going to do a history of functional programming, and I'm sure he'll be telling us how he fitted into that history, because it's a very important part of history. But he originally did his DPhil at Oxford, and then he also worked at Queen Mary College, University of Texas at Austin, and mostly at Kent in Canterbury, where he's still emeritus professor, and he's also an emeritus professor at Middlesex University. So I thought I wouldn't say a lot of things about functional programming because we're going to hear a lot from David, but I thought I'd give a slightly different mini presentation just beforehand of David's academic family tree, which some of you may or may not know. So we're going to start with Alonzo Church and Alan Turing there. So hopefully you've heard of Alan Turing, hopefully most of you have heard of Alonzo Church, but Alan Turing studied under Alonzo Church at Princeton. And then also supervised Robin Gandy, who supervised a number of students. You're not going to see a whole family tree here. But Alonso Church had a lot of students, and one of them was Dana Scott, and Dana Scott ended up in Oxford. A lot of other students there, 5,000 students, and descending from Alonso Church. But at Oxford, David Turner was one of Dana Scott's students, getting his DPhil in 1981. Also studying under Christopher Strachey, who hopefully a lot of you have heard of, who was the director of the Programming Research Group in Oxford. So Dana Scott was in the Mathematical Institute in Oxford, but there was a lot of toing and froing with Christopher Strachey and the Programming Research Group. So you can see that basically Alan Turing is David's uncle. I don't think they ever actually met, but it's nice to have somebody from such good breeding. And actually, also interestingly, this is the Peter Landin Semantics seminar. And although Peter Landin never did a doctorate, and Christopher Strachey didn't either, Peter Landin was an assistant to Christopher Strachey, so I put a little dotted line there as Peter Landin sort of studying with Christopher Strachey. So a sort of, I guess, brother, or with Peter, or half-brother, so I've actually done a little bit of work on looking at Alan Turing's family tree. So this, and as you can see, I've slightly doctored this by adding David in there from the paper. So this shows you a bit more of the structure of Alan Turing's tree with David Turner in there too. But then if you go back, this is all on the mathematics genealogy project, which is great if you want to follow these things. I love just following back, see where it leads to. So if you go back from David and Alan, you get to Alonso Church, and then you go through various people in the US, in Yale, Chicago, and then you suddenly flip over to Europe, you get to France, and we keep going back, and then you start seeing names you may have heard of, like Poisson, you may have heard of, and then we start to see some names. So hopefully a lot of you know all these names with Euler or Euler, as was said in the film, but actually Euler, Bernoulli, etc., and then all the way back to Leibniz. So I think David comes from a pretty impressive background in his family tree, so he's got excellent genes, I think, to talk on functional programming. So hopefully we're going to hear a very interesting talk on the history of functional programming from David. Thank you.
Well, I'd like to begin by thanking the FACS committee for inviting me to give this talk. It's actually quite an honour to be giving a seminar named after Peter Landin. I did have the privilege of being in the same department as Peter Landin for a year when I was a visiting professor at Queen Mary in 2000 to 2001, and we had a number of interesting conversations. But Peter's influence on me goes much further back. When I was a PhD student in Oxford in 68 to 72, I eagerly read all of Peter Landin's papers about lambda calculus and their connection to programming languages, and they were then quite hot off the press. And Christopher Strachey, who was my supervisor, had a close connection with Landin because Christopher founded one of the first software consultancies in Britain, which later became Capgemini, I believe. And when he made some money out of software consulting, the first thing he did was to employ Peter Landin as an assistant, and he paid Peter Landin to do research on lambda calculus. Peter had a strong, Peter's papers, especially the next 700 programming languages, which I'll mention in a minute. Oh, have I got the thingy for changing slides? Had a strong influence on my work in designing programming languages over the next 2 decades. Let me just see, that's the right way around, yeah. I find it confusing having 2 screens. I feel I should have 2 me's on each side. I want to talk about the history of functional programming languages of a certain kind, of which Haskell is the most widely used current example. That is, functional programming languages that are purely functional, strongly typed, and lazy. That is, support non-strict functions by default. A non-strict function is one that can return a result even if one or more of its arguments is undefined. We'll start with the lambda calculus, which is the foundation of functional programming, and then I want to look at what happened in the 1960s. Lisp, which is famous as effectively the first functional language to develop a serious user community. Algol 60, which has important connections to the lambda calculus, which Landin first noticed, and IceWin. These are all things that happened in the 1960s. So we're going to look at that. Then I'm going to look at the work that I did in the 1970s, making a practical vehicle for functional programming in a lazy language, and also making sense of programming with lists. And then I want to look at what happened in Edinburgh in the same period. My languages in the 1970s were typed lists, meaning any type checking happened at runtime. There was no type checking by the compiler. Meanwhile, in the 1970s in Edinburgh, extremely important work was done on static type systems, including the invention of the polymorphic type discipline of Milner. I brought together, I stole those ideas from Edinburgh and put them into what I had done in the 70s to create Miranda. And Miranda was an important ancestor of Haskell. How many of you have used or know of, I say have used Haskell? That looked like about 2/3, at least half anyway, yeah. Okay, right. So, is that the right way? Yes, let's begin with the lambda calculus. The lambda calculus emerged in the late 1920s as part of an attempt by Church, Curry and others to create a new foundation for mathematics based on sets rather than, based on functions rather than sets. The attempt founded on a paradox discovered by Curry, which was essentially the same paradox that brought down the original typeless set theory, namely the Russell paradox. But what survived out of this failed attempt was a simple and powerful theory of pure functions. So the lambda calculus was a typeless theory of pure functions. It had three formation rules. A term was either a variable, and I'm using lowercase letters for variables, or an application of one term to another, and I'm using uppercase letters for terms, or the abstraction of a variable from a term, for which Church used the notation lambda x dot, and then the body of the term. And the intuition is that lambda x dot b, let's say, means that function of x which returns b as its answer, b presumably being a term with some occurrences of x in it. There are just three laws which create a theory of what Church called the theory of lambda conversion. Alpha conversion says that systematic change of bound variables is always permitted and the term is essentially the same. Two terms that are the same up to change of bound variables are said to be equal up to alpha conversion, and that's an important notion. The second rule says that you can apply a function to an argument by carrying out, I'll have to choose one of them to point at, this operation, the square bracket, substitute term A for variable x in term B is a very important operation, and it turns out that to avoid unwanted variable capture, you may have to do several alpha conversions on A or B as you go in to stop, otherwise you can get problems that turned up, interestingly, in the first version of Lisp, which shows that McCarthy should have read to the end of Right. With this seemingly very meagre apparatus, you can make functional representations of almost any data you can think of. So how do you represent numbers? Well, you say, for example, that the number 7 is that function of A and B that applies A 7 times to B. And you represent a pair as it's lambda x, y, z, z, x, y is a pair. I don't know, how many of you have played with the lambda calculus and done this kind of thing? Yeah, lots of you. Okay, so you know you can represent any kind of numbers, pairs, lists, anything, as functions. 3 important results about the lambda calculus. The first 2 known at least by 1950, probably earlier. The Church-Rosser theorem is a confluence result. It says, imagine you've got a term which has a bunch of read x's in it. A read x is the left-hand side of eta or beta. That's a beta read x, that's an eta read x. The rule eta says the function that applies A to its argument is just the same as A. It's a weak form of extensionality. Right, if you have some term A, which you can reduce in 2 different ways to, let's say, B or B dash, you can bring B and B dash back together by doing the right reductions and get a confluence. And that's quite difficult to prove, but it was proved by Church and Rosser, I think probably in the 30s. Do you know when it was first proved, Simon?
30s.
Probably in the 30s. There's a much slicker proof discovered about 1970 by Jean-Jacques Levy and David Parr, which is the one that is taught now. Anyway, that's a very important result because it implies that normal forms are unique up to alpha conversion. And the second Church-Rosser theorem tells you how to find the normal form if there is one. Just keep hitting the leftmost read x. That's called normal order reduction. That's guaranteed to find the normal form if there is one. And that has interesting implications if you try and implement a programming language based on the lambda calculus, because it means that you have to, if you look at rule beta, if you're doing the leftmost read x, it means the leftmost read x, let's say this is the whole thing, the leftmost read x here is this one. Even if there are read x's inside A, you don't do them. You do the big one first. And that means that means lazy evaluation. It means you substitute the argument into the function body without first reducing it, which is not the obvious thing to do. The obvious thing to do is call by value, reduce the argument first. The third result, which was discovered by Corrado-Bohm in 1968, or proved, but I think people suspected it earlier, proved by Bohm in 68. It's a sort of separability theorem. It says that if A and B are terms with distinct beta-eta normal forms, you can find a context which turns one of them into first and the other one into second. This lambda xy dot x, that means lambda x dot lambda y dot x, you can call that first, you can call that second. So that means you can separate A and B into any 2 distinct terms that you want. And what that tells us is that beta-eta conversion is the strongest possible equational theory on normalizing terms. Because if you added a single extra equation between normalizing terms, you would be able to prove that 1 equals 2. Okay. Now, at this point I want to make a detour into lazy evaluation. As I've already pointed out, normal order reduction, the second Church-Rosser theorem tells us that if we want to always find the normal form of a normalizing term, we have to substitute actual parameters into function bodies unreduced. Practical implementations of functional languages from 1960 onwards, starting with Lisp, actually didn't do that. they reduced the argument to its value before passing it into the function, because that's the obvious thing to do. Otherwise, you're going to have to reduce it as many times as it occurs in the body. However, it's call by value is an incorrect reduction strategy if you're trying to implement the lambda calculus. Wadsworth, who was a student of Strachey in the year before me, he was in Strachey's first batch of PhD students, I was in the second, so I did know Wadsworth and talk to him. He showed in his thesis, which is called The Semantics and Pragmatics of the Lambda Calculus, that you could overcome the efficiency disadvantage, at least in principle, by working with graphs rather than trees. So you can have shared sub-expressions, and the redexes inside the shared sub-expression only have to be reduced once, because it's pointed at from as many places in the graph. So that was a big step forward, and then that gave me the idea of doing the same thing for SK combinators. And I learned about SK combinators from Dana Scott, who gave a wonderful series of lectures on combinatory logic when he arrived in Oxford in '69, I think that was. So I had a high-level language called Sassel, which was a sugared lambda calculus, and I showed that I could compile it to SK combinators and then execute the resulting combinator code using combinator graph reduction, which is slow compared with what Haskell can do now, but was fast compared with what people had at the time. The next step, which was discovered simultaneously by several people, Leonard Augustin and Thomas Johnson at Chalmers, but also John Hughes in Oxford, rather than using a fixed number of what we might call small step combinators, like S and K, you extract big step combinators from the program source and then compile down to assembly code, or eventually machine code, but actually doing those steps on a graph. So you're getting compiled graph reduction to implement lambda calculus. And this was further developed by Simon P.J. into the spineless tagless G machine. The only step he didn't make was making it heapless as well, because then there would have been nothing left. And the Glasgow Haskell compiler, or Great Haskell compiler, can be used for production programming. So over a period of 2 decades, normal order reduction of the lambda calculus was turned into a practical tool for serious software. So let me go back to 1960, in fact to 1958, when McCarthy invented Lisp. Lisp was essentially the first functional language, or the first with a serious user community. Lisp, what time did I start? Time myself a bit. Right, Lisp was designed for doing computation on symbolic data. The first serious application in Lisp was a symbolic integration program, quite a difficult artificial intelligence problem. So that gives you the idea of the kind of domain that McCarthy was aiming at. The S language was a data language. It had just atoms and pairing, nothing else. So an atom was just a word stored in compressed form in the computer, and you could build trees or graphs or anything with pairing. Pairing was your only structure. It was called cons, short for construct, I suppose. And each pair had a car and a CUDA. Car stood for contents address register, and CUDA was contents decrement register, which was just the instructions that you happen to use. We would now call it head and tail. Right, and then there was a pencil and paper language called the M language, which was essentially an implementation of Klee's first order recursion equations. You could write recursive functions which had conditional branching and const, car and CUDA. And that is enough to define any computation over S expressions. And McCarthy showed that an arbitrary flowchart could be coded in the M language. And the next step was to represent the M language using S expressions. And you have a function called eval, which interprets an S expression as an M language program and does it. So there are two things going on here in Lisp. You've got first order recursion equations, but you've got eval and quote. You have the ability to express programs as data and to treat data as program. And that's very powerful, but it's another layer of stuff different from what the lambda calculus is expressing. So what we have is a first order language that is made, I would say, pseudo higher order by using metaprogramming. And I'll tell you what goes wrong here. You're not doing alpha conversion when you do the substitutions. You get unwanted variable capture. And this became known as the Funard problem and drove Lisp people mad for about 5 years. And initially, McCarthy thought it was a bug in the eval program. And at this point, he must have read Church's paper to the end and realized that it was a language designer. So, where did I get the, sorry, I want to get to, no, I'm going the wrong way. Oh yeah, not until Scheme in Sussman, 1975, did versions of Lisp appear, so it actually took 15 years with static binding. Okay, so that was a major confusion. So I wanted to, yes, some myths about Lisp. Let's just do that. People, by pure Lisp, people mean Lisp, the purely the functional part of Lisp. Well, pure Lisp never actually existed as a separate language. Lisp began as a dialect of Fortran, and it had assignment and goto before it had conditional expressions and recursion. And Lisp programmers made frequent use of mutating data. Replacer and replacerer were changing fields in a data structure. It was only a few crazy theorists who tried to write purely functional programs, but it was interesting that you could. Second myth, Lisp was not based on the lambda calculus, despite using the word lambda. McCarthy's inspiration was actually Kleene's theory of first-order recursion equations. He got the word lambda from Church, but as I say, didn't at that time study the calculus of lambda conversion. And I've explained the problem about free variables. You get dynamic binding. So if you define a function that has a free variable y in it, y gets bound to whatever happens to be around in the context where f is called, whereas it should get bound to the y that is around in the context where f is defined. And that's essentially the same make as defining the same mistake as forgetting to do alpha conversion when you do your substitution. Okay. Right. Meanwhile, on the other side of the Atlantic, Algol 60 actually got alpha conversion right, even though it's an imperative language. If you read the Algol 60 report, which is written by Peter Nauer, it is a masterpiece. It's in ordinary English prose, but it's a masterpiece of precise technical writing. And if you read the part where he explains the calling mechanism, what happens when you substitute actual parameters into a function body, and remember that Algol had call by name, which means the argument was passed into the function unevaluated, that was the default. And Nauer's description of that mechanism is exactly a description of the substitution operation of Church, including doing alpha conversions when you need to. So insofar as getting the binding rules right, Algol 60 was actually closer to the lambda calculus than Lisp. Randall and Russell, there's a famous book, The Implementation of Algol 60, described their implementation. Algol had the property, had nested procedures, and you could pass a procedure to another procedure as a parameter, although not returned as a result. Implementing that required careful attention to free variables, and Randall and Russell invented something called the static chain, which was, you have a stack of the frames of successive function calls, but you have the static chain jumps down the stack in big jumps because it connects each stack frame to the stack frame of the textually enclosing function, not the function that called it. Sorry, functions were called procedures, and never mind. Now, if functions can be returned as results as well as passed in as parameters, then a free variable can be held onto after that stack frame has been pushed off the stack. Landin, who was interested in implementing the lambda calculus, solved this problem in his SECD machine by storing functions in the heap as closures. The closure being a pair consisting of the code for the function and a pointer to the right place for its free variables. And that was a crucial mechanism. Closure, yeah. I should have said about Lisp, the most important thing about Lisp was the invention of garbage collection. In my opinion, that's even more important than its connection or than its slightly muddled collection to the lambda calculus. McCarthy had the foresight to refuse to clutter his algorithms with storage, allocation and disposal housekeeping. And to get that detail out of his algorithms, he had to invent heap storage and automatic garbage collection, which I think was his most important, inventing Lisp was pretty important anyway. Yeah, inventing garbage collection was an added bonus. Right, so closures live in the heap, are garbage collected when they're not wanted, which solves the problem of functions being able to survive the place in which the death of the frame in which way they were created. Peter Landin wrote a series of papers about lambda calculus and programming languages in the 60s, one of which was the mechanical evaluation of expressions, which invented the SECD machine and closures. Another one was the next 700 programming languages, which I and other people found very inspiring. He describes a language family which can be specialized to an application area by a suitable choice of constants and basic functions, but the basic ideas are that you have syntactic sugar which avoids the need for lambdas. Landin called this church without lambda. So you have let and rec and where, and you can say things like this: expression where y of x equals stuff and g of y equals other stuff. And you can write quite complicated lambda expressions, but in a readable form, and you don't see a lambda anywhere. He also invented the idea of using layout to express nested block structure, so you don't have to clutter your code with begin end or lots of brackets. That's a plague in Lisp, is the number of brackets that you get. Strachey had a joke that said that Lisp stands for lots of irrelevant and silly parentheses. Okay, and then to this apparatus of church without lambda and a nice layout, he added mutable variables and assignment, and also a very strange thing called the J operator, which allows a program to capture its own continuation, which is an idea that turned up later in Lisp as call current continuation. But Landin had this thing in 1965. It was called something like It wasn't further adventures with jumps and labels, but it was something with jumps and labels. Yeah, so the J operator, nobody ever implemented it, ISWIM as such, but the nearest was a language called PAL, used for teaching at MIT, which had all the main ideas of ISWIM in it. Art Evans, who invented PAL, used first-class labels instead of the J operator, and they're actually much easier to understand. You can set a label and then jump to it after the code in which the label was set has died, which means you're backtracking into an earlier incarnation of a function. It's very powerful. You can do lots of strange control structures. And I studied PAL for my PhD. Joe Stoy brought back the implementation of PAL from MIT, and Strachey suggested that I try to implement it efficiently. And I spent 3 years failing to do so. And the killer was the first-class labels, or essentially the J operator. There's no way to implement that efficiently. It means you can't throw anything away because it might be jumped back into. However, I learned a lot about languages and implementation. So in 1972, I left Oxford with my PhD unwritten and went to St Andrews, and in the first term I gave a course on programming language theory, and in the course I invented a blackboard notation which was essentially the applicative subset of ISWIM. And to my surprise, a colleague, Tony Davey, went away and implemented it over the weekend. He implemented it in Lisp. I hadn't met Lisp before. So because it had been implemented, we had to give it a name. So we called it SASL, which was St Andrews Static Lambda. St Andrews Static Language. Maybe we should have called it St Andrews Sugared Lambda, because it was a straight sugaring of the lambda calculus. I made two innovations. Multi-level pattern matching. So they had the idea you could express a structure, but putting variables in the leaves of the structure, and then match that against the data structure, which gave you a way of binding names to parts of a complicated data structure in a transparent way. And I also decided to make string, not to have string as a separate data type, but a string would just be a list of chars, because a list of characters, because then you can use your list processing apparatus to do string mangling as well. It was call by value. It delayed its typing to a runtime. It had no lambda. It used let and rec and sugaring like that. But it was very lambda calculus in flavour. It had curried functions with left associative application and so on. And it was used for teaching functional programming at St Andrews instead of Lisp. And along the way, I invented a package of list processing functions, map, filter, fold right, fold left, and a bit later, list comprehensions. So the list processing apparatus in Haskell, the basis of it was already there in SASL in the 1970s. So what were the advantages? I used SASL for teaching a course, which before I got to St Andrews had been taught in Lisp, course in functional programming. The advantages were the syntactic sugar, which made it easier to write programs. That it had the correct, from the beginning, it had the correct scope rules for free variables, because it really was based on the lambda calculus, and at that stage, Lisp was still struggling with the fun-arg problem. And multi-level pattern matching turned out to be a real win in terms of readability. So here is a Lisp expression which picks apart a pair of pairs and puts it back together in another pattern. And this is what it looked like in SASL. In this pattern match, your pattern matching, see, this is the shape of X. You name the parts and then put them together in a different way. That's now very familiar, but I hadn't seen that before. And was quite proud of it. In 1973, SASL was probably unique in having these properties. Why was SASL, like Lisp, dynamically typed. People called these languages type lists. They weren't type lists, they did type checking, but they did their type checking dynamically at runtime. Well, languages that work with symbolic data, like Lisp, and Sassel was also working with symbolic data mainly. I wasn't doing number crunching with arrays, you do that in Fortran. You need structural polymorphism because a function which reverses a list or traverses a tree doesn't need to know the type of the elements. You can move elements around without knowing what they are because you're not actually processing them, you're just moving them. Well, in fact, you're not moving them, you're traversing a structure and creating another structure. Before Milner's 1978 paper, the only way to handle this was to delay type checking until runtime. That was the only way to get the right kind of structural polymorphism. But Milner showed that you could have a static type discipline that expressed polymorphism. You know, you can say there's a reverse function is of type list of alpha to list of alpha, where alpha is a type variable. It's quite a simple idea once you see it, but it took someone like Milner to invent it. There's actually a trace of it already in Curry and Fays. There's a type system. Curry and Fays is the 1958 book on combinatorial logic. Has an enormous amount of ideas in it, and one of them was the germ of the idea of polymorphic types was already there. Okay. Oh, so here's a nice example of the kind of tricks you can play with runtime typing. This f is a function of an unknown number of arguments. It's a function from truth values to truth values. You can write this two-line test if it's a tautology. Depends on the fact that the function is curried. Because you can ask it, are you a function? Are you a Boolean? And if it is, that's the answer. And if it isn't yet a Boolean, you know you've got to apply it to some more arguments. So you have a sort of branching tree here, which creates all possible rows of the truth table. It's very difficult to do that in a language with static typing. Sassel evolved over the next 10 years. I repackaged the pattern matching to do multi-equation function definition, which was an idea I got from John Darlington. List comprehensions also turned up, which was also based on an idea of John Darlington's, which I'll come to in a minute. Just be careful not to spend too long on this early stuff. Right. List comprehensions, which you've probably all seen, they're in Haskell. They first arrived actually in a language called KRC, which was a kind of experiment. It was a miniaturized version of Sassel in which you could only write one-line equations. I was trying to invent a functional equivalent of BASIC. It doesn't quite work. It was an interesting experiment, but list comprehensions came out of that. With lazy lists, these become very powerful. And these are all the sites that were using Sassel by 1986. People were quite excited by lazy evaluation. Why is lazy evaluation so good? And Sassel was the first language with a serious user community that was lazy. Other people had lazy languages, but they tended just to run in one site. Sassel actually got to about 30 sites, as you saw. First of all, for consistency with the theory of lambda conversion, if you always want to find the normal form, if there is one, you must do lazy evaluation. Secondly, it supports equational reasoning. If beta reduction holds without exceptions, that means you can substitute equals for equals without worrying about bottom being a special case. It renders exotic control structures unnecessary because anything you can do with coroutines, you can do with lazy lists. Because what would have been the other coroutine You have two coroutines who talk to each other. Well, one of them is the main program, and the other one is just the description of the list. The list that is unfolding as you look at it. You turn the other, the partner coroutine becomes data, in effect. And the list of successive methods replaces backtracking, which is another clever control structure people do with call current continuation. But in a lazy language, you don't need it. There's a famous paper by Wadler of 1985, replacing a failure by a list of successes. The idea was already there, but people didn't have a name for it. And it's amazing what a difference it makes, giving something a slick name. People started using it much more after Wadler's paper. But looking back, I could see the idea was already there in the 1976 Sassel manual. I just didn't have a name for it. Okay, so OKRC was a miniaturized version of Sassel, where list comprehensions came from originally. And I experimented with this notation instead of conditional expressions. It's guards. So you have conditional equations instead of conditional expressions, and that made its way into later languages, as we will see. Right. Meanwhile, what was happening at Edinburgh while I was inventing a lazy functional programming language was important work on types. Birstall's 1969 paper, Proving Properties of Programs by Structural Induction, showed how you could add algebraic, what we now call algebraic data types, to ISWIM, and he invented a case switch where you do pattern matching of an expression against different patterns and choose the alternative that matches. And John Darlington, who was Rod Birstall's PhD student, invented a language called NPL, for New Programming Language, that had simple function definitions like this, using pattern matching and multi-equation definitions, which is where I got the idea and put it into Sassel. And NPL also had set expressions like this. Set of even big X is the set of all n in big X such that even n. Right. His set expressions they weren't lazy. What I did was I changed the sets to lists and made the lists lazy. And then the idea becomes much more practical, because you can create the set of all elements of this list without actually having to spell them all out. You don't actually do anything until someone asks for the head of the list, and then you give them the first even one. NPL was used for work on program transformation, which was some nice results published by Darlington and Birstall in the mid-70s. NPL evolved into HOPE 1980, which was higher order, strongly typed, had polymorphism with explicit types. It was purely functional, had multi-equation pattern matching, but dropped the set expressions, which were, in a call-by-value language, are not very practical. Also at Edinburgh, Robin Milner and his colleagues invented the first version of ML, which stands for meta language. It was part of a project to build a system for implementing Dana Scott's theory of computable functions. The meta language was used in which to write the tactics in which to construct the proofs in Dana Scott's logic. But it became of interest in its own right. ML, which stood for meta language, had a type system. The types were built using type sum, type product, and type recursion, and it also had type abstraction. It was call by value. It had no pattern matching. You analyze structures by tests, and is left is right. But it had polymorphic typing with type inference. Standard ML is the confluence of the HOPE and the ML streams, but it's not pure. it's widely used, it has a functional subset, but it also has mutable data and indeed exceptions. Okay, so Miranda was really the marriage of the lazy functional programming language that I invented in the 70s at St Andrews and then brought to Kent. The marriage of that with the polymorphic type discipline that had been developed at Edinburgh. So Miranda was as I say there. This was the notation I used for types. I copied ML. ML used sequences of stars for type variables. So one type variable was star. If you needed two type variables, they were star and star star. It begins to get cumbersome. Here's a function called zip3 that comes from the prelude, the standard environment of Miranda. You can guess what it does from its type, can't you? It takes three lists and zips them together to create a list of triples. However, the types are beginning to get cumbersome, and I haven't shown you zip6 because it wouldn't fit on the slide. Okay, Miranda introduced a lexical distinction between variables and constructors to distinguish pattern matching, like this, node xy equals stuff, which binds x and y to parts of stuff, which must be constructed with the node constructor, whereas foo_xy, with a small letter foo, is just defining a function. Okay, so that distinction carried over into Haskell, as people will know, and Haskell generalized it to types as well, which was a good idea because it got rid of those wretched stars. Because I had guarded equations rather than conditional expressions in Miranda, and I wanted to have where, I had to change the scope rules for where. So instead of qualifying an expression, you can have something like this, and the where definition, sorry to people on that side of the room that I keep pointing over here, the scope of the definitions is the whole right-hand side, including all the alternatives and their guards. Okay, and Haskell uses where in the same way, and Haskell also has let to qualify expressions. Because I'm a sort of minimalist, I like to have only one way of doing each thing to keep my language as small as possible. I just had where. Miranda, I say is rather than was, because it still runs. And if anyone wants to run it, the source code and other information is at miranda.org.uk. I've decided to many years later than I should have done, I've put it under a BSD license, which is a do what you like open source license, and it's at that website. So Miranda, purely functional, has list comprehensions, the package for doing list processing that it got from Sassel with fold R, fold L, take while, drop while, all that stuff. It has optional type specifications and type inference. It was first released in 1985. It was implemented by a compiler to SK combinators and then an SK combinator reduction machine, with subsequent releases in two subsequent releases. And it was quite widely used until the mid-90s when it began to be replaced by Haskell. So now let's look at Haskell. And yes, I've got about 7 minutes left. Stick to the hour. Right, maybe I should favour people on this side. Haskell has many similarities to Miranda. Much of the syntax is the same, but there are two immediately visible changes. The guards, you have guarded equations, but the guards are switched to the right-hand side, sorry, I'm the wrong way, to the left-hand side, I'm the wrong way around. The guards are switched to before the equals. And that is rather logical, because what happens is you could have a pattern over here, and then the guards are refining the pattern into subcases. And so it's logical to have them near each other. It was a useful innovation. And the other thing is Haskell took the uppercase, lowercase distinction, which I used on data, and applied it to types as well. So uppercase tree is a data type, lowercase a is a type variable. And that, there we are, look at zip, here's zip4, which wouldn't have fitted with my star notation. You can see immediately what's going on without having stars in your eyes. It's a very simple change, but I kicked myself for not having thought of it. Almost everything in Miranda is present in Haskell, but Haskell, first of all, has a richer syntax. It's not a minimalist language. It has guards and conditional expressions. It has let and where. It has pattern matching by equations and case expressions. But that's just syntactic sugar. The more important thing, it has major new features. Type classes, monadic I/O, and nested modules. And the only thing I have time to talk about is type classes, which is the most important single innovation. Type classes are very powerful. They greatly extend what you can express in a static type system, but they also greatly add to the complexity of the type system. Type classes are an organizing principle where all kinds of things that are otherwise anomalous can be brought together into a hierarchy of classes. For example, the fact that complex numbers can be added and subtracted and multiplied and divided, but they can't be compared by greater than and less than. And there's an interesting hierarchy of number types that express this kind of thing. So the class structure gives you another layer of organization. Here's an example of what you can do with types, a surprising thing. I went around telling people that they couldn't do the Sassel tautology example in Haskell, and they said, oh yes, we can. And here it is. It's a little bit, you have to understand classes quite well to follow what's going on. There's the Sassel code, and this is doing the same job in Haskell by inventing a whole class to represent what this function is doing. And in fact, that particular example won't compile on a standard Haskell compiler unless you give it... The Glasgow Haskell compiler is like a Swiss Army knife. It has a blade for everything. Just paraphrasing a remark of Nicholas Beert about PL1. He said about PL1, which was a very large language invented by IBM, it has a blade, it's like a Swiss Army knife. It has a blade for everything, but you'll cut your hand off trying to get it open. I don't think Haskell's as bad as that, because Simon PJ is a very careful programmer, as are the rest of his team. But anyway, it turns out that this, one of the many flags to GHC, this one will let you compile this example. You can actually write the tautology example in standard Haskell, but it's about twice as long and at least twice as hard to understand. So you could say that type classes are too clever for their own good, is a possible line to take. Yes, so let me end with this remark about Haskell. An early meeting of what became the Haskell Committee, this would have been about 1988, the language didn't have a name yet, drew up a set of principles, including, this was principle 5, I think, the language was called it at this stage, should be based on ideas that enjoy a wide consensus. Type classes were an obvious exception to that. They were not. It was a new idea that no one had seen before. So there was a certain risk in putting it into the language. It turned out to be very powerful and very useful as an organizing principle, but here is the downside. It's a concept invented by Wadler a little bit later. A language is coherent, in Wadler's terminology, if the computational behavior of a term is independent of its type. A simple example is that ++ is the append operator on this. Nil ++ nil computes to nil, and it doesn't matter if it's an empty list of apples or an empty list of bananas. But that should apply everywhere. where a term, a more complex term than just the empty list, can be read at more than one type, coherence means its computational behavior is independent of the type that the context forces it to have. Haskell is not coherent by design, because type classes enable you to change the behavior of a term based on the type of its context. And in particular, it has overloaded constants. And here's an example of the problem. I don't know if it's a problem, it's a lack of coherence in what is. So we set n equal to 1, and p is the length of show n. Show n is a string, which expresses n as a numeral. By default, you have p equals 1. But if you add a type specification saying that n is of type float, then the length changes to 3, because at type float, show 1 gives you 1.0. And if you instead say that n is rational, which is one of the built-in types of Haskell, p suddenly becomes 5. The issue here is overloaded constants. 1 can mean 1.0, it can mean 1% 1, it can mean something bigger at type complex. I don't think you have a type complex rational in Haskell, but if you did, it would be even bigger at complex rational. So, interestingly, something I've wondered about on and off over the years, there's a paper by Wadler, which he did a few years later than the paper in which he invented type classes. It's called A Second Look at Overloading, jointly with Oderska and Veer, in which he invents an alternative that is a system of overloading that is coherent. And the key is there are no overloaded constants. Now that would change Haskell quite a lot, but I've often wondered what the type class system would look like if it was based on Wadler's second attempt at inventing type classes rather than his first. So I commend that paper to anyone interested in type classes. And then I've got a bunch of references which are on the slide so people can look up all the references if they want. I won't talk about that oddity in Haskell because I've used up my hour. Sorry, that was a rather quick scan through about 40 years of programming language history. But I will stop there.
Thank you very much, Dave, for that tour de force. I see we've already got a couple of questions, so who had their hand up? Yes.
Thank you very much for the talk. I read an anecdote from Olivier Danville, I think, who said that he asked Peter Landin and John Reynolds whether they felt the evaluation order of denotational semantics meta-language was call by value or call by name. And they disagreed, Peter saying call by value and John saying call by name. I wondered if you had an opinion on that.
Oh, I think it's called by name. Yeah, definitely. In fact, one way I've had of understanding what I'm doing with languages like Sassel is turning the meta-language of denotational semantics into a programming language. And I always assumed from the moment I first saw the meta-language, and I'm sure Strachey intended it to have a normal order semantics. So, which one of the pair was it? Said it was called by value?
Landin said call by value.
I'm really surprised by that.
That's what Danville says anyway.
Yeah. Does Danville take a side?
No.
No. Well, I think John Reynolds was right. And I'm almost certain, no, I am certain, because I sat through Strachey's lectures on denotational semantics. He was assuming normal order lambda calculus.
Great, thank you.
In fact, we'll just do this one first then. Yeah.
So, question about polymorphic strictness. So in Haskell, it's the SEQ operator, and I was wondering if that feature was in Miranda, and when that idea came about.
So, sorry, swallowed some water the wrong way. Say again the feature.
The feature where you can strictly, in a lazy language, like Miranda or Haskell, but you can strictly evaluate something even though you don't know what its type is, or it is polymorphic.
Oh yes, yes, Miranda had that. Yeah, I had two things. Seq, S-E-Q,
Right, okay.
which said, return the first thing as the answer, but evaluate the second thing before you do it. And I'm not telling you what the type is. That was in, and I also had another thing called force, which said, here's a data structure, evaluate it right down to its leaves, whatever it is.
So in that case, I have a follow-up question, if you don't mind.
Yeah, yeah.
Which is, so did Miranda then have the, what was the strictness property of fold L?
Right. Following a suggestion by Richard Bird,
Yeah.
I cheated and put an SEQ into fold L so that it would not use up lots of heap.
Right.
Yeah.
That's in the prelude, right? That's in the Miranda prelude.
Yes, yes.
Because there's two ways of doing it, and I think Haskell's got it wrong.
What does Haskell do?
Well, okay, for starters, Haskell didn't choose to have fold L being strict, like, right? But
No, that's right, I
But
remember.
it has a fold L prime which does.
Yes.
But there's two ways that you can choose to do the strictness in fold L.
Oh, yes.
It makes a difference, semantically and...
Yeah, yeah. No, I do remember someone pointing this out to me, and whatever was the right one, I did that one. At least that's what I'm claiming. Well, as Miranda, the Miranda sources are now online, you can have a look and see what it does. And if it is in fact the wrong one, please tell me.
Jeremy.
You were talking about, David, you were talking about miscomprehension. Actually, I should say first, you said 40 years, it's really 60 years if you go back to Lisp in 1958.
Oh yes, because we're now nearly at 1920, aren't we? Yeah, right.
20.
Sorry, 20. Yeah, sorry, I thought my mind was back sometimes. Yeah.
But I had a question about Lisp comprehensions. You were talking about, you had them in, you introduced them in your languages first in KLC, is that right?
Yes, and then they got into Sassel by about 1983.
Right, later.
They weren't initially in Sassel.
Right.
No.
But you learned about them from John Darlington in NPL.
I took John Darlington's set expressions and thought, well, what will happen if we make these lazy?
Sure.
And then I decided that removing duplicates was an irrelevant complication, so they were lists, not sets.
Yeah. So
Yeah.
there's a language and a line of work called Settle from
Oh,
NYU.
Yes, yes.
Jack Schwartz and I forget the others.
Oh yes, no, that took up the idea of set expressions and went much further with it.
Well, I looked into the history of these, and it's there. There's a big monograph called On Programming by Schwartz and others from NYU in 1969 that has essentially NPL's set comprehension construction in it. So.
Oh right. Oh okay. No, I hadn't seen that.
Do you happen to know whether John Darlington knew about Settle?
I don't think he would have done, because John Darlington, this would have been the early 70s. I went to see John, I was at St Andrews from 72 to 77, and I went to visit John Darlington several times. I never heard of Settle until the 1980s.
Right.
And I'm assuming that John Darlington would be the same.
So that this was an independent invention?
It must be a code, yes, must be independent. Yeah.
Thank you.
I've come across co-recursion. Never really studied that, but it does seem to relate to lazy evaluation. Could you elaborate on that?
Yes, I'm not an expert on that, but co-recursion is sort of the dual of recursion. So if you're constructing a lazy list and you want to be sure that the list always has a next element, that it doesn't fall into a black hole, there's a set of rules that you can apply which are sort of, there are rules for well-founded recursion, that you've got to be descending on something. And there are rules for productive co-recursion, that guarantee that there is always a next link in the chain. And that's actually a harder problem. One approach is a theorem by de Backer, which says you construct a metric space, you construct a metric on your data, and you show that what you're doing at each stage of the co-recursion is a contraction operation, meaning that the distance between 2 points in this funny metric space gets smaller. I mean, that's quite a technical approach. I can't remember the name of the paper. It was but am I missing the point of your question? I'm feeling I might be.
Well, as I say, I haven't studied co-recursion.
Okay. I mean, I think I was probably talking, co-recursion and co-induction go together.
Yeah.
And I realised I was really talking about co-induction, which is how do you prove that a co-recursive depth is productive. Jeremy knows much more about this than me.
And he's about to tell us.
Go on, Jeremy.
Early on you talked about church encoding of data types, so there are church encodings
Yes.
of actual numbers and church encodings of lists and so on. Does that work for code data types as well? Is there a church encoding?
Oh, I believe it does, yes.
Strings?
Yes. I saw somewhere an article about that, and I've racked my brain several times recently trying to remember where this article was. But yes, there are church encodings of code data, and I wish someone would remind me where this paper is. So you haven't seen it?
Sounds familiar.
Burge might be Burge's book on
I've got a copy of that. Which I haven't
loads
opened.
of stuff. I mean, it's a treasure trove.
Yeah, I'll look in there.
Like parser combination, there was a Twitter discussion.
Yeah.
Oh, there's parser combinations already in Bird, isn't
Yeah.
there? Yeah, and that was 1975.
And I think there might be stuff about.
Yeah, okay, that's a good place to look.
And
Yeah.
Burge worked with Landin in New York.
Oh, I didn't know that.
Yeah.
Oh, yes, because I knew that Landin worked at one of the IBM research places. Was it Yorktown Heights, maybe, or?
Yeah, I can't remember now.
But that would have been where he met
Yeah,
Birch,
they
because
did,
Birch
yes.
was with IBM.
Yeah.
Yeah. Apparently the origin of that book, Recursive Programming Techniques, is that after years and years of Birch beavering away at functional programming and no one understanding what he was doing, his manager said to him, well, what are you actually producing? You know, we'd like to know. So he wrote the book.
Yeah. Well, it's still producing.
Yeah.
Yes.
So are there any practical coherent languages, programming languages, in the sense that you were talking about?
Well, Miranda was very nearly coherent. The only exceptions are things that I could easily have fixed. So I think ML is probably coherent as long as you avoid the imperative features. That's a very good question. If I redo Miranda, I will make sure it's coherent.
So doesn't that mean that you can't do equality generically and printing generically?
Well, what ML does about that is it has essentially a built-in type class, which is equality types.
So the string you get from
So if you try and show a function, it would just say that's a type error.
sure, but
Because
the things you can show, you show differently. You show the behaviour of show is determined by the type.
yes.
So how can you show one coherently?
Well,
they don't have
wait a minute. If you're doing this coherently, the number 1 will always be integer. If you want float, you have to write 1.0. And if you want rational, you have to write 1/1. The key to coherence, or part of it, is not having any overloaded constants. In fact, if you have overloaded, you can have overloaded functions as long as the overloading is separated by the type of the first argument. But you mustn't, and because a constant doesn't have a first argument, it can't be overloaded. The second Wadler paper, the one by Odersky and Wadler and Ware, goes into this. It's quite lucid, as Wadler's papers always are. Yeah.
Yes, in today's time there's large-scale distributed systems, and there begins to be talk about software, hardware co-design. I'm wondering if functional programming could be helpful or particularly relevant in doing efficient and robust implementations.
Yes. You mean that
So for example,
hardware co-design,
yeah,
you
so
would do a better
it's-
job on
It's
functional
very
languages?
parallel, and SRAM could carry computing units, so you
Yeah.
could begin to do computing on blocks of memory and reduce that. So
Yeah, sure. I mean, in principle, that sounds right, but the details always turn out to be hard. I mean, I was examiner to a PhD thesis a few years ago where the guy looked at extracting concurrency from, I think they were Sassel programs. But, well, one thing is you have to write the program in a special way if you want it to be highly concurrent. Picking up another part of your question, there was an attempt to design chips. Right, when VLSI came out, and there was that book by Mead and Conway that made it sound as though everyone could design their own chip, which turned out not to be as easy as the book made it sound. Sussman, for example, at MIT, designed a chip for doing beta reduction blindingly fast. Is that the kind of thing you mean?
could be, or even large.
But it was sequential. Yeah, what you're thinking of is
Okay.
doing lots of reductions in parallel.
If you look at what's happening in the FPGA world right now, there's a lot of work on translating C code and C++ code directly into hardware implementations. And traditionally, you'd write the code in a language like VHDL or Verilog, which looks like software but isn't.
Yes.
And the idea is that software engineers don't understand hardware, unless they're really weird like me, and people write algorithms in C or C++ style languages, have those automatically translated into hardware accelerators. There's a lot of work going into that.
Okay. But that should be easier if you're starting from a functional language.
It should, but of course the idea is to take languages that people are using at the present moment and make it easier for them.
There's a company that designs chips, which was started by Arvind at MIT. I can't remember what the company's called, but they have a language called BlueSpec, which is a functional language for designing chips. It's sort of vaguely Haskell based, I think.
So I said Joe Story works there.
Yes, I knew that. Yeah.
Okay. Over here.
Now you've open sourced Miranda, do you have any hopes or ideas of what people might do with it to extend the language or add new things to it that you might not have the time for?
Well, I guess one of the consequences of making something open source is that you have deliberately given up control of what people might do with it. So it's not my place to tell people what to do with it.
I'm just wondered if you thought, oh,
Yeah.
I would do ABC next to, you know.
We don't have a to-do list with it.
Well, I think what I want to do is rewrite the Miranda compiler in Miranda, so it's then much more portable. And I think open sourcing that would be a much better service to the world, because if I rewrote the Miranda compiler in Miranda, it would be about 5 times smaller and much easier to understand than all the grubby C code. Yeah, so I think my job would be to, which I've been meaning to do for years, but maybe I'll finally get around to it, and that is rewriting the Miranda compiler in Miranda. Yeah.
Any more questions?
Actually, just while I was talking about hardware, one thing that occurred to me earlier, when you talked about that language which had first-class labels, you said that doesn't work because you've got to keep track of everything and you can never throw anything away.
Yes.
Are you aware of the work that's been done on reversible computing to reduce energy consumption?
No, I'm not. Well, I've heard of it, but I don't know any of the details.
Okay, basically the idea is that entropy in the information theory sense and entropy in the physics sense are very, very deeply the same thing. And when you do computation, if you take 2 plus 2 and get 4, you take 1 plus 3 and get 4, effectively what you're doing is throwing away information. 4 has less information in it than the original sum. That consumes energy which can never be recovered. But if you keep everything so that you could reverse it, in principle, you can do that with no net consumption of energy. And that's sort of still very much lab stuff, very much theoretical stuff, but it's a possible solution to the fact that we have reached the point now where getting the heat out of chips is the physically most difficult thing about making computers faster.
Yes, as I understand it, the reason that chips haven't got any faster since about 2005 is the heat dissipation problem.
And the idea of reversible computing, in principle, is that you can get rid of that heat dissipation and suddenly you've got new open vistas. But that obviously involves never throwing anything away, and that just made me think of...
Yes. Well, I don't know if this is related, but there's an idea in databases of a database that only ever grows. You never throw anything away. So, and that fits with functional programming, because instead of changing the data, you just grow a new branch, which is, this is what it looked like on Tuesday, but Monday's is still there. I mean, do you think that's related?
It's not directly related, but I think if you have got reversible computing where you never destroy information, it's the same kind of idea.
Right.
I used a database in, I guess, the end of the 80s, early 90s, more APL-ish inspired, but it never destroyed anything. Every piece of data was a time series.
Right.
Well, not quite regular time series, but everything was over time. So you only ever added stuff, and all the queries, which again didn't look like SQL, more APL-ish, you could literally write a piece of code, and you could say as of, and give it a time, and it would literally do exactly the same expression and dig through the data at a particular time. It was really, really clever.
Yeah.
Yes.
That sort of thing has become much more practical as storage has got cheaper.
Yeah, and then it was quite difficult then, because the computing power of the disk space was limited. But it was a really clever idea, coming to it from functional programming, seeing that, like, oh yeah, these guys, they live somewhere in Boston.
So what was stored, what was kept in the database?
Everything.
The entire universe.
Well, anything you put. When you'd add stuff into the data, I can't remember all the things, but you'd add stuff at a particular time, so please add this, and it would automatically add it to the stream of stuff for that particular structure, so it never threw anything away, you never updated anything, because there was no concept of updating, there was only, here's this new value at this time, and because you had conceptually hundreds or thousands of streams of data, any expression would always be cut across time. So stuff would be true from when it got created to the point at which the new one came. So you could say, give me the value of this stuff at midnight. And you didn't have to have a piece of data created at midnight like you'd have to do with SQL. You know, if you want to say what's the value at midnight, if you don't have a timestamp at midnight, you get nothing because it doesn't match. Whereas in that one, it had a concept of stuff living over time.
So basically, instead of 2 details, time as a dimension.
Yeah.
GitHub works like that. GitHub works like that.
Oh yes.
Okay. Wikipedia works like that.
Well, they do now, but in those days, that whole idea was quite interesting.
Anyway, thank you very much for a wonderful work. We can continue outside. We've got some refreshments, food, etc. Our next meeting is the 27th of February, so I hope to see some of you there. You might enjoy some of the digital art on the walls, which is a new feature here. My other hat is involvement with the Computer Arts Society, so do enjoy the nice pictures too.
I went to talk 3 years ago came to present some results from some PhD studies. Forgive me for giving the the idea was time series data and produce
I think it must be
And the
80.
benchmarks tend to produce
It's
progression. There are various tools of study. One of the tools that she was what they do is they use their computers to match together on a variety of specifications, and they wrote a specification. Developed a specification